This presentation contributes to a number of training videos made as a part of the MPR Biosmet project in 2023. My name is Nielsen and I work as a physicist for the Danish Technological Institute. The aim of this presentation is to introduce some basic metrology concepts. The presentation is split in two videos. Part 1 that introduces the concept of metrological traceability, and you will find this presentation in another video. In part 2, this video, the concepts precision, accuracy, and measurement uncertainty is explained. In part 1, the concept of metrological traceability was introduced in a historical perspective. You heard how measurement units are defined and realized in practical measure, and how systematic calibration is used in order to control the quality of measurements. We learned that metrological traceability is a property of a measurement result, whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. Now I will continue to explain the concept of measurement uncertainty, why we need it, and why it is necessary to know in order to make decisions based on measurements. Please let the red dot in this target surface represent the true value of a quantity, and the green dots individual measurement results, that is, attempts to determine the true value. The measurements are scattered around the true value, but the measured quantity value, that is the mean value, is not far from the true quantity value. We can say that the accuracy is good. The replicate measurement, that is the green dots, is quite scattered, and we can say that the precision is poor. In the second diagram, the scatter of the replicate measurements are small. We can say the precision is good. On the other hand, the mean value is not close to the true quantity value. We can say the accuracy is poor. In the third diagram, the scatter of the replicate measurements are small. The precision is good. And the mean value is close to the true quantity value, and that means the accuracy is also good. In the fourth diagram, we are in a very bad situation with poor accuracy and poor precision. When we as metrologists develop measurement systems or measurement instruments, we strive for precision. When we have obtained a satisfactory precision, we can calibrate our device by comparison to a measurement standard and directly determine the systematic measurement error. We can then apply a correction and obtain the situation in the second diagram. The scatter of green points around the red dot is now a measure of the quality of the measured quantity value. The measurement uncertainty is a non-negative parameter that characterizes the dispersion of the quantity values being attributed to a measurand. Measurement uncertainty comprises, in general, many components, including components associated with corrections and the assigned quantity values of the measurement standards. To uncover all uncertainty components can be a circumstantial affair. By calibrating a measurement instrument, the error with respect to a reference is found. This measurement has an uncertainty. An example from the calibration certificate of a relative humidity sensor is seen here. You will find back the error and the uncertainty of the error in the two last columns. Now I can introduce a calibration hierarchy. The calibration hierarchy illustrates metrological traceability. You see a sequence of calibrations from a primary measurement standard, that is the realization of the definition of the unit, to the final measuring system, where the outcome of each calibration depends on the outcome of the previous calibration. For every step in this chain of calibrations, the uncertainty increases, and too low uncertainty breaks this traceability chain. But why do we need to know the measurement uncertainty? We need it to make decisions based on measurement. Let me give you an example. Alice and Bob is driving. We measure that Alice drives 53 kilometers per hour and Bob drives 56 kilometers per hour. Let's say our measurement uncertainty is plus minus 1 kilometer per hour and plotted in a diagram. Here it is easy to conclude that Bob is fastest. In the second case, our measurement uncertainty is plus minus 7 kilometers per hour. We plot again the measurements in the diagram. Now the situation is more difficult. Taking into account the uncertainty, there's a good probability that Alice is actually fastest. We see that it is difficult to conclude differences between measurements, and there's a risk that we make the wrong conclusions or decisions. A good guideline taking a risk-based approach on the use of decision rules when declaring statements of conformity to a specification or standard is available from the ILAC website. It's called ILAC G8. There's many ways to do this, but on the next slides I show some examples from this guideline, just to introduce the concept. This figure illustrates a similar dilemma as was presented in the Bob-Alice case. There's two identical measurements, but with different measurement uncertainties. The measurement uncertainty in the lower result, case A, lies entirely within the tolerance limit. The upper result, case B, has significantly larger measurement uncertainty. The risk of falsely accepting a result in case B is higher due to the larger measurement uncertainty. In this example, we only look at the measurement and disregards the uncertainty. The two first measurements are within specifications and the two latter out of specification. But looking at the second and the third measurement and the uncertainty, it is evident that there is a risk of false accept or false reject based on the measurement. The question is, how do we control this risk? One method is to introduce a guard band. We reduce the acceptance limit with W. Looking at the new acceptance limits, we see that the first two measurements gives a pass and the two last results in a fail. By choosing this guard band wisely, we can control the risk. The ILAC G8 gives an example on commonly used guard bands. Typically, the guard band is determined as a factor multiplied with the expanded uncertainty of measurement. For example, the guard band can be set equal to the expanded uncertainty, which then results in a probability of false accept less than 2.5%. This is very useful. Now we are close to the end of this presentation. We learned that metrological traceability is a property of a measurement result, whereby the result can be related to a reference through a documented and unbroken chain of calibrations, each contributing to the measurement uncertainty. Measurement uncertainty assures that a measurement result is related to a reference on a higher level that in the end is compared with a primary realization of the unit. Remember the calibration hierarchy. Measurement uncertainty is a measure of the quality of the measurement. Thus, traceability is needed in order to make trustworthy measurements on all levels independent of method and instrument type. And this is exactly what the BioFmet project is trying to solve for biofuels measurement. In the BioFmet project, we have worked on all levels of the calibration hierarchy, from primary realization of units, development of transfer standards and reference materials, sampling, and industrial measurements. Similar to this presentation, my colleagues from the project consortium present what we have learned in the project. I hope you'll find all these presentations useful. If you want to know more or get in contact, you're welcome to visit our website or follow us on LinkedIn.